Hello everyone, today I will introduce you to our project 1. My name is Zhu Jiahao and my partner is Yang Hang. First thing is MOSFET characterization. We use this two circuit to do the characterization. And the first thing is gate voltage sweep. This is gate voltage sweep current in linear coordination for MOSFET, and we curve this we feed this curve like from 0 to 0.5 in log coordination to get the derived slope of copper over UT, and we get all the data from the curve fit. And for PFET, the thing different is we curve it from like 1.7 volt to 2 volt, which is some threshold area. So we use this some threshold current equation and derive it to get the slope copper over UT, and then again we got all the data. For the source sweep, it is different, but we still use the substrate current equation and derive it to get like a straight line and do a curve fit. Actually get to a very ideal UT. For the PFET, it's the same thing, especially just the area of the curve fit is different. Okay, this is summary of our curve fit and parameters. For the copper, for the NFET is 0.56 and the PFET is 0.61, and the I0 is a little different, but the I0 for the PFET is derived from the curve fit, not from just reading the data. So I think that's because the I0 is a very small number. So basically, a little difference is what happened for the I0. And VTH, we mainly depend on reading the curve, which when the curve takes a sharp turn, it's possibly the VTH. So we just derive it from the curve directly. And the UT we counted at both 26 millivolt. And basic transistor circuits, that we have common drain, common source, and OTA. For the common source, because for the source follower, which is a common drain amplifier, we derive from some subthreshold current equation, and then we can find out the transfer function of it, which is the copper is the linear part and another part over Vin. And it's the same thing for the common source, which has a linear part of minus copper over sigma, and another part over sigma times V. And the OTA is a major low-pass filter, so it basically derives the transfer function from this picture, which we think there is a load capacitance and a load resistance. So we just derive this by utilizing the OTA in an open loop structure. So this is what we get. It's basically a low-pass filter transfer function. The source follower is we do that in this infrastructure, which is a DC voltage connect to the drain, and the gate we swipe the gate voltage and measure the source voltage. We change the drain voltage for 3 different values. The blue one is for 1.5 volt, and the green one is for 2 volt, and the red one is for 2.5 volt. So basically, we can see that changing the volts of the drain will not just change the line a lot, but the source follower will function like after the gate voltage is above like 1.2 volt. By curve fit the curve between like 1.2 and 2 volt, we get the gain, which is copper, for the two situation. The data is not very different, so it's around like 0.84 or 0.9. I think the the relationship between copper and the source voltage also means the relationship between the copper and the gate voltage, because for source follower, the source voltage is always connected to the gate voltage. For the first part here in this picture, below the 1 volt, we can see from before that the source voltage did not change. So at this time, actually the copper has this picture is like we used the data in this picture. By deriving the line here, we use 2 points to get to the data and just minus it, and we get the copper in the finally. So basically, we can see when the source follower function properly, the copper will not change dramatically. When below 1 volt, because we can see from the picture of VGS, actually the below 1 is VGS is not actually much bigger than the threshold voltage. So basically, we can see that after the VGS is stable here, the copper is stable. So I think the major difference between the copper is not lying the relationship between copper and the source voltage is behind is between copper and maybe the difference of gate voltage and source voltage. For the common source, we do a rough scan, which is from 0 to 1 volt. And there's some step here. I think it is because the minimal step of the circuit measurement system, since I do like I used an increment of 1 millivolt, but it didn't turn out to be functional when I use this kind of small increment. So we plot the V out and the gain. The gain how we get the gain is we minus the drain voltage 2.5 and divide. We use the output voltage to minus the drain voltage and then divide it by the input voltage, because it's the inverse amplifier, so we can get a gain. And the flying scan is also showing a very strange step curve, and we also get it again. But for the gain around the subthreshold area, it's very stable around the 11. And this is the comparison picture of these two scan. And for the transconductance amplifier, we do a linear follower, but actually it turned out to be the same, but it still shows some step effect because I think it is because some kind of measurement limitation. And for the step effect, we don't find we don't find obvious effect of like the curve or like change slowly, because I think we may made a mistake when we set up the sample rate. We set up a sample rate at about 100 hertz, which actually is very small. So for a small step, which is around 0. Actually, it's around 18 millivolt. So the output is very bad, but it suits well for the follower actually. For a big step, it will show exactly what the square wave will be. But because of the frequency is very low, so we didn't find so obvious like effect of the low pass filter. Thank you.